The infinite monkey theorem states that a monkey hitting keys at random on a typewriter keyboard for an infinite amount of time will almost surely type any given text, such as the complete works of William Shakespeare. But what if we took that theorem and applied it to throwing monkeys at a goal? Recently, my wife got into Super Monkey Ball speedrunning for fun. This joke resulted in her now holding 3 separate world records. In my competitive nature, I wanted to take one of these records from her, but I am garbage at the game. So, to maintain some of my pride, I decided to do the next best thing: train a computer to beat the game for me. So, what is Super Monkey Ball? Super Monkey Ball is a niche series where monkeys in balls move through a course and cross the goal line. However, instead of traditional games where you control the character, you're actually controlling the stage, tilting it so the monkeys roll across the stage. Like the Tilt Maze toys you may have played with. Wait, do kids still play with these toys? Hold on, let's see if they still make them. Oh god! Okay, same concept, but I don't remember them being this complex. Anyway, Monkey Ball. Monkey, ball, tilt stage, goal. How hard can it be to train a computer to play this game? When I first started brainstorming this project, I was immediately reminded of Seth Bling's Mario project, where he used a neural evolution algorithm called NEAT to teach a computer how to play Mario. Check it out if you haven't. He will probably do a better job at explaining the technology than me. But please come back here when you're done. Cool. Alright, so now I'm going to run through the techniques and technologies used to program this AI. If the programming aspects aren't really your cup of tea, please ignore me and enjoy a video of my dog Macy going for a walk. Oh yeah, baby! YouTube retention, let's go! Alright, like with Mario, this project utilizes NEAT, or Neural Evolution of Augmented Topologies. NEAT makes use of neural networks, but applies the concept of natural selection and evolution. A neural network has a series of inputs and outputs. In this example, the inputs are chunks of a screenshot of the game, and the outputs are the different directions you can move with the joystick: up, down, left, right, anywhere in between. A standard neural network has a bunch of these connections that map the inputs to the outputs. These connections have various weights and activation functions, and then the weights and thresholds for the activation functions are adjusted based on the training of the network. Without diving too much into the specifics, since there are plenty of better explanations out there, the network performs a series of calculations through these connections, and based on these calculations, gives an output. The way NEAT changes things up is that the network starts out without any connections. Instead, the resulting network is based on the process of mutations and natural selection. To build the network, we create a population of monkeys, where each monkey in that population has a randomly generated genome. The quote-unquote code of a monkey's genome determines the makeup of its network. Some may start off with a naive connection of, say, this section of the screen being blue means go forward, while others may not have any connections and therefore not move at all. Think of the network as an individual's brain, pretty much driving their decision making. So we take this population of starter monkeys and throw them into the game. Oftentimes, you'll find most, if not all, monkeys don't move at all, like they don't even know how to move. In any case, we score each monkey on their performance in a metric known as fitness. Then we evaluate the population as a whole. This is where natural selection comes into play. We organize the population by their fitness scores, taking the top 10% performers and then killing off the rest. Which means 90% of the monkeys were not fit for survival. Sorry, bud. With the remaining 10%, we breed the next population. As is with real-world reproduction, there is a small chance of mutations within the next population. This mutation chance changes the genetic makeup of a monkey. In this case, changing the network, potentially giving them a survival advantage. Mutations can be anything from a change of weights in the connections to the creation or removal of connection altogether. We continue this process of fitness evaluation and repopulation until, eventually, we have a network complex enough to properly play the game. Now, since I don't have infinite time, I included the functionality of having a species of monkey going extinct if its fitness score stagnates for too many generations. If we face a full extinction, then we'll be left with the best performer overall. But how do we evaluate each monkey's performance? I'm glad you asked, hypothetical viewer. Generally, in Monkey Ball, you have 3 end conditions: goal, where the player crosses the goal; fallout, where the player falls out of the stage; and time over, where the player did not reach the goal in time, but stayed on the stage. It's very easy to assign positive and negative points to each of these end conditions, but that alone doesn't provide the evolution process enough information to determine a given monkey's fitness. So, how do we differentiate between two different monkeys that both got time overstate? I knew I wanted to reward the monkeys for at least getting close to the goal, so I looked into how to quantify that. Unfortunately, no matter where I looked, it did not seem that the Super Monkey Ball game tracks how close you are to the goal, as it's ultimately meaningless for the actual game. And I wasn't about to build the game from the ground up just to include that metric, so I decided to get creative. If I could build a system that could detect where the goal is and calculate how far the player is from the goal, I could incorporate that metric into the fitness function. And then I found YOLO, You Only Look Once. Despite the algorithm's silly name, it is quite a powerful region-bound object detection algorithm. In short, the YOLO model evaluates a given image and returns whether a specified object is present, along with a region where that object is located. Not only is it effective, it is incredibly fast. And for a program that needs to run in real time, this was perfect. I trained and loaded up a YOLO model into the project, and it worked like a charm. Now, I determined how close the goal was by taking the area of the bounding box and dividing it by the total area of the image. The percentage that the goal takes up of the screen can loosely be interpreted to how close it is. While not perfect, it still provides a metric for differentiating between two monkeys' performances. Additionally, I wanted these monkeys not only to cross the goal, but to do it quickly. So, for those that crossed the goal, they got a bonus added to their fitness based on how quickly they did so. Putting it all together, we calculate the monkey's fitness as follows. If a monkey falls out of the stage or runs out of time, we take the closest point it got to the goal, calculate how much of the screen the goal occupies, up to 50%, and subtract 25 as its penalty, giving us a fitness range of -25 to 25. If the monkey crosses the goal, we start by giving it a bonus of 30 as a reward, and then award extra points based on how quickly it reached the goal. To calculate this, we take the max time of 60, subtract how long it took, then apply a 1.25 times modifier. This gives us a fitness range of 30 to 105, where 105 effectively means the monkey instantly reached the goal, which shouldn't be possible. So, with all of that, all that's left is to set the monkeys into action. First off, welcome back to those who are captivated by Macy. I hope the technical explanation wasn't too overwhelming, and to those who did pay attention to the explanation, I hope it wasn't too terrible. Right, so, the moment you've been waiting for. Ready to see the monkeys in action? Alright, let's go! Oh. Okay. Wait, just give them some time. They're still learning. Okay. Well, maybe we'll speed this up a bit. There we go. Now they're doing much better. I ran the evolution process through 3 stages: Beginner Floor 1, Beginner Floor 2, and Beginner Floor 7, each with varying degrees of success. Beginner Floor 1 is by far the simplest stage in the game. It even has rails to prevent you from falling off, though it is still possible with enough effort. The solution to this stage is as simple as hold forward, nothing else. So, it should be no surprise that the AI quickly figured out this solution. Based on my testing, the highest possible fitness score to get on this stage is approximately 101. Running the evolution program, the AI hit the target fitness early within the second generation. As you can see in this graph, the results are not all that interesting. So, to get a better idea of how the evolution performs, I decided to do a second run with a new goal. Get the population's average fitness as high as possible. In this run, I set the target average fitness to 95, but the population just barely missed it, reaching a maximum average fitness of 93.1. After over 200 generations, I decided to call it there. All in all, still a super successful run. Floor 2 is very similar to Floor 1, but adds the extra challenge of having the player dodge the gap in the center. There also is a secondary goal underneath the stage that will warp the player ahead a few stages. However, it was unlikely the AI would ever reach that goal, so I ultimately ignored it. From my testing, I could get a maximum fitness score of just under 100. So I set the target fitness to 99.5 and started the simulation. The monkey population did surprisingly well early on, reaching a fitness score of 91.5 on Generation 8. However, the population did not really excel until around Generation 74, where the population was consistently reaching a maximum fitness of over 90. Unfortunately, the population peaked at 98.7 in Generation 105, then stagnated around 94 from there. I noticed the monkeys tended to do this zigzag movement towards the goal, which greatly slowed them down. I think the population found it to be a safer strategy that maximizes fitness and reduces the chance of falling off in the middle. Because of this, I decided to end the simulation at Generation 322, as it was already running for over a week straight. While the monkeys did not reach the fitness target, I did observe something interesting. As I mentioned previously, the monkeys frequently did this zigzag movement, but what's more interesting is when they missed the goal, almost consistently, the monkeys would swing back around for another lap, clearly showing that they were recognizing the stage and making clear efforts towards reaching the goal, compared to other monkeys blindly flailing about until they either fell off or timed out. Seeing this phenomenon is exactly why I find this topic so interesting. So, Floor 7. Yeah, this was a bit of a stretch. I asked a bunch of my friends who are fans of Super Monkey Ball. There are surprisingly more than you think for such a niche game. I asked them which stage the monkeys should tackle next, and this is what they voted for. Now, this stage is a major step up from the previous two, no pun intended. It comprises of 4 levels, separated by ramps on alternating ends of the platforms. Additionally, each ramp is steeper than the last. From a human's perspective, this is a relatively simple stage. It really just tests your ability to make sharp turns. With my admittedly mediocre skill level, I could get a fitness score of between 89 and 92. I wasn't sure how well the simulation would handle this stage, but I set the target fitness score to 90 and hoped it would surprise me. But before I go into the final results, let's roll back a bit. Earlier, I went through how the fitness was calculated. However, I glossed over a detail in my process. I mentioned that fallout and time over were treated the same in the calculation. This wasn't always the case. When first brainstorming this idea, I figured it would be best to differentiate between a fallout and a time over end state. My thought was that if it stayed on the stage and got a time over, it was a better result than fallout. Therefore, I gave the fallout state a harsher penalty. For floors 1 and 2, this made very little difference. However, on floor 7, this encouraged the monkeys to stay on the first platform and not risk going up the ramp and potentially falling out. See, while recording footage for this video, I streamed everything to my friend group's Discord server. One of my friends, Christian, religiously watched the monkeys as they tackled these stages. One day, he pointed out the flaw in my fitness calculations. I was distinguishing between the 2 end states where, in the game, it makes virtually no difference. Realizing this, I took his advice and changed up the fitness calculations and restarted the simulation on floor 7. At first, not much had changed, but then, about a day into the simulation, it happened. Okay, it didn't make it to the goal, but it got really close compared to the rest of the generations, that is. This was huge. I continued the simulation, holding out hope. Unfortunately, nothing really happened. The monkeys never crossed the goal, and after over 500 generations and oh lord, almost 500 gigabytes of footage? Yeah, I was done. This project took me about 4 months to develop and finalize, but it was a lot of fun to work on. It may not be perfect, but it taught me a lot about AI and real-time analysis. I do have a Git repository containing the full project if you're interested in taking a look at it yourself. Full disclaimer, I didn't design it for general usage, so there may be some tweaking required to get it working on your own machine. However, I may come back and update this project over time if I ever feel like it, so please do leave feedback on it. Be nice though. I might cry. Anyways, I'm pretty happy with how this turned out, and I hope you enjoyed it too. If you're watching this video around the time of its release, I'm streaming the AI on Twitch, running different stages. If you'd like to watch it in progress, go check that out. Link in the description. If you did enjoy, please consider leaving a like, maybe subscribing while you're at it. I've got lots of project ideas for the future and would love to share them all with you. If you have an idea on what sort of project I should tackle next, let me know in the comments. Thanks for watching, everyone.